Okay, so if we have the unit circle, we've seen that we have arcs of length 1 over 2 to the n minus 1 pi at step n. And the angles that we can get corresponding to the arc distances that we can get by repeating these small intervals will give us angles of p over 2 to the n minus 1 pi and arc lengths on the unit circle of equal measure. Okay, if we go a few steps more than we've gone here. Okay, we've divided the circle into 32 parts. Another step, we're going to have 64. Another step, 128. Then 256, 512, and after 5 more steps, we have 1,024 points on this curve. Okay, now 1,024 points, those points are going to be really close. They're going to be so close that if we don't have fairly good eyesight, we're not even going to be able to see the distance between them. And if we go 2 more steps, we aren't going to be able to see the distance between them. We don't have enough receptors in our retina to do that. So that these points actually appear to blend together into a continuous line. However, there's always some space between them, whether we can see it or not. And no matter how many times we subdivide, there's always going to be space between these, between the points on this line. Now, it's not going to take too many more subdivisions until we have so many points that the distance between them is less than the separation of 2 atoms. Okay, that is going to take less than 20 more subdivisions forward down to the atomic level. And then we can keep going beyond that. In that sense, we're going to say that the points that we get from this subdivision process become dense. They're dense, but they don't include all points on what we want to call the sine curve. They don't include all points. We won't have included all the points on the circle because, well, let's think about it for a minute. The arc distance to any of those points, any of the points that we can construct, has to be of the form p over 2 to the n minus 1 times pi. Again, p over 2 to the n minus 1 is rational. Multiplying that by the irrational number pi, we get an irrational arc, or an irrational angle in radians, either way we want to look at it. Which means that, among other things, we're never going to get to a rational number of, we're never going to land on a rational arc, an arc of rational length. This subdivision process won't ever accomplish, let's say, an arc of 2, distance 2. If this is on a unit circle, that's a distance wrapped around the arc. Wrap this distance here around the arc, you're going to end up about here. You're never going to land on a point where the arc distance is equal to the diameter of the circle, okay, or any other rational number. Not only that, but you're not going to get any irrational numbers that don't have denominators that are powers of 2. And there are all kinds of denominators that aren't powers of 2. Any power of 3 or 4 or 5, or any mix. Well, actually, 4, we can't include 4 because it is a multiple of 2, but 3, 5, 7, okay, any odd number in the denominator, well, we're not going to be able to get that arc. So there are all kinds of numbers that we can't get. Even though we can construct a dense set of points on this curve, we can't get every point. So that raises the question of how do we even define the curve if we can't construct it? We can't construct every point on the curve. Well, I'm going to leave the question at that. That's a question for more advanced mathematics, but it's an interesting question that we can understand based on this construction. The answer to the question is we do what's called a topological completion, which means we're going to also include every point that we can get as close to as we wish with one of the members of our dense set. But that's an idea that takes a little bit of getting used to, and we're not going to go into the depth of that. But it's a good question to think about. Okay, so a couple other observations I can make The rational numbers are countable. Now, you might well understand what that means at this point. If not, you will soon. It just means that you can count them. You can put the number 1 with some rational number, the number 2 with another one, number 3 with another one, and you can number them in such a way that you can number every one of them. Okay? You can do a counting number for every possible rational number. And it's not too hard to understand how to do that, although it seems kind of strange that you can because of the way infinities work. You can't do that with irrational numbers, and that's a little harder to prove, but it's still something that can be proved to a good advanced high school student. The rational multiples of pi are irrational, but they are countable. Okay, which means you've got an infinity of arcs, okay, that in a sense exceeds the infinity of the number of points you could construct if you continued this subdivision process forever. Another statement, any angle that we want to talk about on this circle, okay, it's either one of the angles that can be constructed or it isn't. Even if it isn't, it contains infinitely many angles that are constructible, infinitely many angles of the form p over 2 to the n minus 1 pi in any of its neighborhoods, no matter how small. What do I mean by neighborhood? First of all, its neighborhoods. That means whatever the angle is, some neighborhood of that angle. What do I mean by the neighborhood of an angle? We take some angle and we take just a little tiny bit smaller angle, a little tiny bit bigger angle, and all the angles in between, a little tiny bit smaller and a little bit tiny bit bigger, are in our neighborhood, and there will be in that neighborhood an infinite number of constructible angles, of this form. And that's kind of an interesting statement that you try to get your head around at this point, although it might be a while before you can deal with a rigorous proof of that sort of thing. Okay, so that's kind of a preview of where we go with the next clip.